Right, so we're still at rate of change. So I'm going to give you two more examples. And like I said, it's kind of heavy on the physics. So, who's in physics? Anybody? Oh, it is? I don't know about that. I'm sorry. Tell me if this looks familiar. Anybody recognize that? Uh, okay, so this is position. Notice from yesterday the SOT, the position of an object fired, thrown, tossed vertically. Thank you, Mr. Newton. The position of an object fired vertically with respect to time. T is time. So this is S, so S is position. What do you think S0 is? Yeah, initial position. Okay. So we have initial position. What is V0? And then G. That's the gravitational constant. Does it ever change? Not on Earth. Yes, it can change depending on the mass of the object you're standing on. Okay. In our case, this is an acceleration. So that's a metric system, which we like much more. It's more friendly. You can estimate it in our system as well, that we prefer, but I don't. Yeah, I prefer the switch, but we do have expensive at this point. Yeah. Okay. Alright, so this is the general graph of what you're looking at for objects thrown, right? Time over height. The first day of school, we actually started with this kind of thing. In the past, with parabolas, you've had to find the axis of symmetry, find the maximum height, correct? It's kind of a pain in the butt, right? Well, what can you do now? Yep. You can take the derivative, and what's the slope of that line? Yeah, so we would take the derivative, set it equal to 0, solve for t, and you have your maximum. Done. And that's why this calculus is very nice. The math is easier once you learn how to do it. Okay. So let's run through an example here. We're going to go David and Goliath, I guess. So we're going to shoot it vertically. So we're going to have a stone. It's shot vertically. This part is very important. Because if you start to introduce angles, we need to have sines and cosines in the formula. Okay, so this has to be vertical. Okay. I'm a 4-year-old boy here. The stone shot vertically with a slingshot has initial velocity 50 meters per second. That is 1 line, okay. Initial height, 10 meters. I encoded that. On my paper, it says with an initial velocity of 50 meters per second and an initial height of 10 meters. So I translated it for you. Be aware that you'll probably see that word, those words, and you have to interpret that. Calculate velocity t equals 2 and t equals 7. That's not what I'm saying. We have to write the equation out now for position. That's all we have, right? We have the position function. S0 is 10. V0t. And then is that minus or plus? It's minus. I'm pretty sure that object don't fly like this. Okay, I lost the special. Yeah. Okay, 4.9, where'd it come from? Half of 9.8. We're using a metric system. So 9.8 goes in here, and then divided by 2. That's the gravitational constant. Part of the formula. Okay, good. All right, now how can I calculate velocity? Derivative of that. There again, derivative of position is velocity. Hey, what's the derivative? The velocity function is the derivative of position. Nothing. Negative minus 9.8 t. Right, power roll and power roll. Okay, now this is the velocity function. How do I calculate velocity at 2? Yeah, close to it. That's all we have to do now. $30.4. Check the other. What are my units? Anybody else? Oh, what's the derivative of a constant? Bye-bye. Always get used to putting your units on there. You're gonna have to do it when you use it in real life and when you're doing tests. Okay, do S prime at 7 now on your own. Somebody said you Why is it negative?
No, because
That is positive. Velocity has direction, right? Speed is always positive, but velocity has a direction indicator. So if we're starting here, velocity is positive because we're going up. At a max height, velocity is negative, right? So it's indicating that we're headed down. Okay, that's throw it up, positive, and then it comes down, negative velocity. Okay, so this is up, down. Okay, this is what our graph looks like. Something like this, right? Parabolic trajectory. So, how do I know that I have to reach a maximum height? Just based on these numbers. Okay. Which theorem have we addressed this year so far? Intermediate value theorem, okay? So see how this has a sign change? Is this continuous? Yes. Does this have a sign change? Therefore, it has to pass 0. In this case, we're talking about slope, right? So think intermediate value theorem there. Continuous, has a sign change, has to pass 0, right? That was on the test, retake. Okay. When does the stone reach maximum height? But how do you know that? Because I punched in the calculator. Explain it a little bit better than that. Okay, so you're using a bracketing technique, right? You're just kind of saying, well, I'm going to make my interval smaller and smaller until I find a 0. Okay, anybody else? Different technique. Alex?
on the top one, it's 4.9 t squared. So we put 5.1.
How do you know it's 5.1? That's what I'm trying to ask you. How do you get that number? What happens when you get a max height? The slope is 0. So what can I do? I set the derivative equal to 0. That is when the velocity goes from positive to negative, it has to hit 0, right? So 50 minus 9.8t equals 0. Solve that linear equation. A little easier and more exact than yours. It's going to give us the number you want to plug in. So add 9.8, divide by 9.8 is 23 decimal places per units. You make a mistake. Oh, that's fine. So we can truncate around. So you kind of get the idea there? You got to start thinking in terms of what's going on here with slope and velocity. Because those are equivalent terms in this context. There are so many different questions you can ask with these problems. I can't show them all to you. So you have to be kind of a problem solver. Do you want me to show you one more? There are two more examples out of my paper. One can be another velocity problem. You want to see that? The other one's particle motion. I guarantee that's going to be on AP test. So I'm showing you that one. The question is, do you want another particle velocity? So this is called particle motion. So basically what they give you is a particle. It could be, in our terms, they just make it a particle. They don't say it's light, or they don't say it's a marble. They just say it's a particle of some kind. And you can have motion along the x-axis, and they give you a function to define that, or a motion along the y-axis. Okay. Here's something like the position. Is that cluing up your position function brain? A particle in inches. Boo. Moving along. The x-axis. After t seconds, is given by this function. T to the fourth minus 2t cubed minus 6t squared plus 9t. Function. There are tons of questions we could ask here too. I could ask, what is the velocity at t equals 3? I could ask you, when is the particle motionless? When is the velocity negative? When is the velocity positive? What is the position of the particle at time t? Yeah, there's questions you can really ask. You have to think. Position, velocity. We haven't got to acceleration yet, but eventually we'll add that in. So, how would I calculate the velocity at 3? T equals 3. Calculate the derivative. Plug 3 in. You want me to put it on here? Okay, good. Okay, so, different question. When is the particle motionless? Interpretation, velocity has to be 0, right? So, derivative. Alex, what's the derivative?
53 squared minus 30.
Okay. And we know that it has to be 0, right? Anybody do that?
Hey, you can.
I don't know if that's factorable. I don't think it is. So, I don't think this is factorable, but if it is, you remember the techniques we used to factor 4-term polynomials? Grouping. So if it was factorable, okay, I could pull a 3 out of here, right? And that would be 4t plus 3. Okay. And pull a 2 out of here, 2t squared actually. What would be left? 2t minus 3. Do those match? No. Okay, so it's probably not that. But that would be what you would do. Use a calculator to solve that. Put the function in the calculator, find the zeros on the graph. More than likely, you're going to get a calculated problem like this. We need to find the zeros of the function. In fact, pre-calculus right now is doing that exact thing. I taught them factoring and graphing today on the calculator. So you guys all did this about this time last year. Anyway, Nancy did. Okay. This is what I have on my paper. Now, if we're living in the real world, and I have negative time, so probably not gonna answer it. Right? Sometimes you have to think real world here. How would I know what is the velocity negative? So what does the negative velocity mean? Not down, this is the x-axis. So left. Negative is left on the x, right? So how would I know that? Negative velocity. So we know it is 0 at these times, correct? So positive, negative, maybe negative, positive. How would I figure that out? I'm going to plug 0 in for the velocity function. What do I get? Positive 9? I don't even need to know the number. And I plug 1 in because it's easy. Get 4 minus 6, negative 2, and that's going to be negative. Right? And then I'm going to check 3. That's going to be a plug. About 100. Pretty close. Anybody have it? Twenty-seven times 4 is 108. 3 squared is 9 times 6 is 54. 36. That's me positive. So velocity is negative from 0.5. Or positive on the other. So you kind of see the particle move to half a second this way, and it switch direction, and then it switch direction again. Don't ask me the physics behind that. Okay. You okay with those two examples? You can handle them? Think, position, derivative is velocity, or speed, rate of change. Velocity is the rate of change. So, I'll give you the assignment if you're. Yeah. Let me make sure it's the rate of change on here. I did take one of the spiraling dots. I'm giving you lots of practice here. These should just be derivative calculations. Lots of derivative calculations. It's going to become automatic. Tomorrow, we will add acceleration to this mix with the second derivative. We'll talk about third derivatives and fourth derivatives and all the stuff that gives us. Okay?